Good afternoon. My name is Catrice Antoine, and the title of my presentation is Ripe for the Picking, an application of ethylene in the packing industry. The objectives of this presentation are to review background information about the effects of ethylene on plants, discuss the results of absorption on porous materials to control ethylene production, expound on the 5E method and its incorporation to teach the material to students. Ethylene is a hormone that plays an essential role in the growth, development, and storage of fruits and vegetables. Ethylene can be beneficial or detrimental. It is beneficial when it helps to accelerate the ripening of fruit. It is detrimental when it leads to over-ripening and decay. There are two classifications of fruits and vegetables. Climacteric, in which a peak in respiration occurs with ripening and there is an increase in ethylene levels. Pears, apples, and peaches are classified as climacteric. Respiration in non-climacteric shows no intense change and ethylene levels are constant. Grapefruit, grapes, and berries are non-climacteric. Ethylene production can harm the post-harvest quality and the shelf life of fruits and vegetables. The main problem of this study is how to reduce ethylene production in fruits and vegetables to extend shelf life and reduce loss. Control techniques considered to reduce ethylene production include removal of ethylene, inhibition of ethylene biosynthesis, inhibition of action. Some absorbents that are currently used to remove ethylene are zeolites, clays, silica, and activated carbon. However, these materials combine with an oxidation agent and produce potassium permanganate, which is toxic to foods. A combination film using zeolite and chitin has been proposed to remove ethylene. Zeolites are aluminum silicate minerals having a three-dimensional structure with interlocking cages and channels that can trap gas but take in water. Chitin is a non-toxic and eco-friendly polysaccharide that has the ability to cross-link with other materials. The combination of zeolite and chitin creates a material that displays superior properties that may help absorb and control ethylene accumulation. The analytical process. Experiments for this study were conducted multiple times to ensure repetitiveness of measurements and consistency of results. The chitin zeolite combination films were prepared by 5 different methods. Each method consisted of mixing the 2% solution with the clinoptilolite particles, then convective dried and neutralized with 1 molar sodium hydroxide. Finally, the film was freeze dried for 24 hours and stored in a desiccator. The chitin zeolite combination films, DCF and PCF, will serve as controls. They followed the same preparation method, but the drying method was different. The two techniques used to analyze the films were scanning electron microscopy to synthesize and characterize the film to determine morphology. The magnetic suspension balance obtained the ethylene absorption capacity. Water vapor permeability was determined gravimetrically using the ASTM method. Figure 6 shows both of the ASTM E96 methods for determining water vapor permeability. In this study, the water vapor permeability was found using the desiccant method. The fermentational cell had a diameter of 24 millimeters and a height of 13.2 millimeters. It contained 2 milliliters of water. The cell was sealed in place in a desiccator with air circulation with 0% relative humidity. The temperature was kept constant at 25 degrees Celsius and the relative humidity was 30%. The cell was weighed 8 times every hour for one 24-hour period. The data collected was used to create a linear regression, which was used to create a trend line in the plot of weight versus time. The slope of the line was calculated. And finally, the data was used in equation 1 and 2 to calculate water vapor permeability and water vapor permeability rate. In both of those equations, the W is the weight sample in grams, T is the time in hours, X is the film's thickness in millimeters, A is the area of exposed film in meters squared, and delta P is the partial water vapor pressure differential across the film in kilopascals. Results from calculations show that as the water vapor permeability decreased, the efficiency of the films as moisture barrier agents increased. Results discussion. Figure 7 shows the scanning electron microscopy of samples from the study. Sample 1 displayed material with a porous structure with heterogeneous particles of various sizes. Sample 2 had a dense, homogeneous microstructure. Sample 3 had a multitude of layers, which may be attributed to the freeze-dried material. Sample 4 showed a dense structure and some zeolite clusters dispersed on the medium. The micrographs of these samples showed irregular structures with porous folds and clusters, which may be due to the Chitson-zeolite interaction. The existence of pores and cavities is related to permeability. Table 2 shows water vapor permeability properties of Chitson-zeolite composite films. One can infer that PCF has the highest thickness and also the highest water vapor properties. Thus, as the thickness of the film increases, so does the water vapor permeability properties of films. Ethylene absorption isotherms for the 6 materials are shown in Figure 8. It can be inferred from the graph the CZ93L absorbed the highest amount of ethylene, 1.1 millimoles grams at 3 bars of pressure. It can also be inferred from the graph that DCF, PCF, and CZ33 had the lowest ethylene absorption capacities. Table 3 compared the ethylene absorption capacities of different materials under similar pressure and temperature conditions from the current study to reference studies from the article. The reference studies evaluated different approaches to modify zeolite to increase ethylene absorption capacity. Data showed that natural zeolite had a higher ethylene absorption capacity than those on replaced forms. The ZR90, which is the sample from the current study, had a maximum ethylene absorption capacity similar to the material from the reference studies. Significant findings from this study displayed that adding zeolites or drying the film increased the water vapor permeability. All Chitson zeolite combined films tested can absorb ethylene efficiently. The optimal content of absorbent will depend on factors such as ethylene release rate and the absorption rate. The societal benefits of this study show that using Chitson and zeolite combined film can aid preservation and increase shelf life. The findings from the study allow the agriculture industry to make an informed decision regarding packaging, help manufacturers meet the 2030 global challenge of decreasing the loss of fruits and vegetables from the post-harvest chain. Lesson objectives for the instructional component. The learner will be able to define the problem and develop possible solutions, form a hypothesis and write it as an if-then statement, evaluate the effects of ethylene in fruit ripening, analyze and interpret data in a table, and conclude which type of film is most effective in absorbing ethylene. To teach the content of this lesson, the 5E instructional model will be used. The 5E instructional model involves building knowledge from experience and new ideas. This model has 5 steps. The first step, engage. The purpose of this step is to stimulate interest and get the student involved in the lesson while assessing prior knowledge about the topic. For this step, the teacher will use a KWL chart. In a KWL chart, the student completes what I know and what I want to know at the beginning of the lesson. At the end of the lesson or the unit, the student completes what I have learned about the topic. The second step, explore. The purpose of the explore step is to get students involved in the topic and provide them with a chance to construct their own understanding about the topic. For this step, the teacher will use a scenario about Mr. James and his form. In this step, the students will read the scenario about Mr. James and his form. They will analyze the information, determine the problem, and infer why there is a problem. They will determine possible solutions with pros and cons of each solution. They will choose the best solution and determine the consequence of the solution. This information will be recorded on the problem solution advanced graphic organizer. The third step, explain. The purpose of the explain step is to provide students with an opportunity to discuss what they have learned thus far and figure out what it means. In this step, the student will be grouped in think, pair, share groups to communicate and discuss what they have learned with their peers. They will share out or present information via science circles. The fourth step is elaborate. The purpose of the elaborate step is to allow students to use their new knowledge and continue to explore its implications. For this step, the students will participate in a laboratory investigation. The students will form a hypothesis, create a rating chart, investigate, make observations, analyze data, and draw conclusions about the effect of ethylene on apples ripening. The fifth step is evaluate. The purpose of the evaluate step is for students and teachers to assess how much learning and understanding has taken place about this topic. For this step, the students will analyze data in a table and determine which film absorbs ethylene most effectively. They will have to justify their answer. At the end of these activities, the teacher will relate the activities to the study. The teacher will have students to conduct additional research about materials used to absorb ethylene. The student will design an experiment related to which material is most effective in absorbing ethylene. Conclusion: the film tested in this study shows that it can act as an effective barrier to ethylene absorption, making it usable to pack produce, extend shelf life, and reduce loss. Additional research and studies should be conducted to determine if the amount of zeolite in a composite film affects the ethylene absorption capacity. Thus, the results may be beneficial to the food and packing industry.